So to do this proof, we will assume that we have some class satisfying all three properties, and then suppose that there is some ordinal not contained in the class, and produce a contradiction. So if there is some ordinal that is not contained in a C which satisfies these three properties, then this forms a non-empty class of ordinals. We already know that the min of such a thing exists, call it alpha. If, we know that alpha cannot possibly be 0, that is to say the empty set, because then it would be in C. And we also know that it cannot be a successor ordinal, or else 2, the second property, would come to bear on this, and we would reach a contradiction that way. So we are only left to deal with case 3. But after all, if our ordinal, alpha, is neither the empty set nor a successor ordinal, then it must be a limit ordinal. That is to say, there is no beta such that it is beta plus 1. And in fact, I didn't write this when I explicitly wrote down property 3, but this property 3 is stated for all limit ordinals. So so we now have that our alpha, in fact, is not equal to 0, because we ruled that out. It is a limit ordinal. So let us see whether or not this second property holds. Well, Since it is not the empty set, we know that there must exist some gamma in it, and therefore less than it. And this alpha being the min of this set, therefore anything less than it must be included in C. That is to say, not in this set. And there we have it. We have just shown that anything less than it is included in C. So now we have the antecedent of this conditional, therefore we get the consequent, and this shows that alpha is in C, but that contradicts our assumption that it is the min element of things not in C, and we have finished the proof.